Hey there, folks. I'm Josh. I am a senior undergraduate at Harvard studying chemistry, and I'm also part of Harvard SEDS. So today I'm going to be talking about solar array actuation mechanisms. The video that I'm about to present to you is not meant to be a comprehensive overview, but it's just to give a sense of, very broad overview of the problems that are covered in this field and also what sorts of solutions folks are coming up with to solve these existing problems. So to begin, so what is a solar array and what is it doing on a satellite? So solar arrays typically consist of an underlying structure for the deployment of a substantial number of individual photovoltaic cells from the body of a spacecraft. And once it's fully deployed, it's desirable for a solar array structure to provide a lightweight, stiff, strong, stable, and flat platform for the solar cells, which would allow uniform exposure to the sun. So these solar arrays are typically stowed such that they're constrained in a small envelope prior to and during launch of the spacecraft. And then they're deployed to their fully extended configuration, which exposes the maximum area of solar cells once the spacecraft has reached its position in space. And so it's desirable actually to minimize the volume of the stowed package while at the same time maximizing the available solar cell area that can be packaged when the thing is stowed, which subsequently allows for the max power production of the spacecraft. So in sum, it's important for these solar array structures to be lightweight and also very manageable in terms of volume, especially when it comes to CubeSats, which are very small in general. So the next thing we're going to cover are conventional actuation systems. So what folks have been using to deploy these solar array structures. So this is an example of a extendable solar array system, which has been dubbed XSAS by its creators. So as you can see on the diagram on the left, the release mechanism is composed of two hinged release panels and a cutter system. And the cutter system actually refers to these four metal film resistors wired in parallel in a single line of high modulus polyethylene wire. The wire is used to tether the release panels to the power bus structure. And to do this, the wire is threaded between two holes on each release panel, which creates these parallel lengths of wire that span the bus's interior. So it's important, this is kind of an important detail. So each length of the wire rests against two resistors mounted to the top surface of the bus. And so this is important for deployment because to actually deploy the release panels, an onboard power source, usually a 9-volt power source, is shorted across the resistor circuit, which then melts the wires. So this is what's referred to commonly as a burn wire. And so these hinges that you see that are circled on the figure, they are actually spring loaded and can actually lock in place once the burn wire is deployed. So the reason why these conventional actuation systems may not be the most advantageous is because the folding of these rigid panels involve mechanical items like hinges and latches and springs, cables, pulleys, which have to be highly reliable in order to prevent loss of the spacecraft and its payload. If you can imagine, the inability to deploy based off of a failure of any of these components would be pretty costly, and especially in terms of the power producing array. These mechanical components are often clunky and they add weight to the entire system, which is desirable to be minimized. So those are some of the facets of conventional actuation systems. They have been used in space many times and they have flight heritage, but it's time to move on, or a lot of people believe it's time to move on. And one of the alternative or future models that people are proposing are these origami inspired folded arrays. And one of them is shown up here. So the desirability comes in the form of its lightweight and efficient use of space. And so these perimeter trusses are one instance of a foldable array that people have been modeling. So as you can sort of see here, these torsion springs are attached to the truss to bias the truss open. And this is viewable in the diagram on the bottom left. So since these torsion springs bias the truss open, this means that the springs are deflected when the arrays and truss are stored. And so this method of stored strain energy makes the arrays self-deployed or self-deployable. On the rightmost image, you can see these serpentine flexures, which are attached to the array from the truss in order to maintain a 90-degree torsion, as well as 90-degree bend to one side in order for the entire structure to deploy. So that's just one model people are considering. Another model is the model based off of shape memory polymers, which are also these interesting and exciting materials that are being appropriated for solar array deployment mechanisms. So shape memory polymers are these specialized plastics with low transition temperatures relative to the melting temperature, at which the plastic becomes malleable and can be molded into a new shape. So when cooled, the plastic retains the new shape until heated again past its transition temperature. And so the shape memory plastic can be folded into whatever pattern you can conceive of for the array, and then thermally activated to return to the flat or deployed configuration. And so alternatively, you can also have strips of the plastic to be affixed to rows of panels that can wrap around the central bus to deploy the entire structure, which is another alternative. And so these are just a couple of the alternative origami-inspired foldable arrays that people have been trying out in addition to the conventional mechanically actuated arrays. Again, this is a very short presentation regarding some of the general ideas that have been floating around this field, but hopefully these have been informative in eliciting some maybe new kinds of thinking or new ideas if you're interested in this sort of field. So thank you all again for listening. Hope you enjoyed this presentation.